Have you ever used a camera flash or heard a speaker thump with power? Behind the scenes, that's the magic of capacitors at work. A capacitor is a simple but powerful electrical device. It stores energy in the form of an electric field, just like you might store water in a tank. It has two conducting plates, and between them lies a gap filled with insulating material called a dielectric. When we connect this setup to a battery, something interesting happens. Positive charges accumulate on one plate, while negative charges build up on the other. This separation of charge creates potential energy ready to be released when needed. We define this charge storage ability with the equation Q equals C multiplied by V, where Q is the charge stored, C is the capacitance, and V is the potential difference. You'll find capacitors used in almost every circuit. They help smoothen out power supplies, filter noise in radios, and even help your phone's processor operate efficiently. So, how do we measure a capacitor's ability to store charge? That's where capacitance comes in. It's defined as the amount of charge stored per volt of potential difference. The formula is C equals Q divided by V. Capacitance is measured in farads, named after the famous scientist Michael Faraday. 1 farad is actually huge. Most everyday capacitors have values in microfarads, nanofarads, or even picofarads. Capacitance doesn't just depend on the material, it also depends on how the capacitor is built. Specifically, it depends on the area of the plates, the distance between them, and the dielectric material in between. For a simple parallel plate capacitor, the formula becomes C equals epsilon naught multiplied by or divided by D, where A is the plate area, D is the distance between them, and epsilon naught is the permittivity of free space. In the visual here, each variable plays a role in determining how much charge can be stored for a given voltage. Let's dig deeper into what affects a capacitor's performance. First, the plate area. A larger area means more space for charge to sit, more storage, more capacitance. Next, the distance between the plates. The closer the plates, the stronger the electric field, and thus a greater ability to store charge. Now comes the game changer, the dielectric material. When we insert a dielectric between the plates, it doesn't conduct electricity, but it affects the electric field in a fascinating way. It weakens the field slightly, allowing even more charge to accumulate without increasing voltage. This effect is captured in a revised formula, C equals K multiplied by epsilon naught multiplied by or divided by D, where K is the dielectric constant of the material. For example, mica has a K value around 6. So, using mica in place of air increases capacitance by 6 times. This is why choosing the right dielectric is crucial when designing a capacitor for a specific job. Capacitors come in different shapes and sizes, not just the flat parallel plate version. The parallel plate capacitor is mostly for theoretical understanding and precise instruments. Then we have the cylindrical capacitor. Imagine two coaxial cylinders, one inside the other. These are common in high voltage applications like power transmission. And then there's the spherical capacitor, made with two concentric spherical shells. Its capacitance depends on the inner and outer radii. The formula for a spherical capacitor is C equals 4 pi epsilon naught multiplied by R1 times R2 divided by R2 minus R1, where R1 is the radius of the inner shell and R2 is the radius of the outer one. Each design serves a specific purpose, and in the diagrams here, you can see their structural differences clearly. Now let's explore how capacitors behave when combined. Just like resistors, they can be connected in series or parallel. In series combination, the total capacitance is less than any individual one. Here, we use the formula 1 by C equivalent equals 1 by C1 plus 1 by C2 and so on. In this setup, all capacitors carry the same charge, but the voltage gets divided. On the other hand, in parallel combination, capacitors are side by side and share the same voltage. Their capacitance simply add up. C equivalent equals C1 plus C2 plus C3 and so on. Let's take an example. If you have a 4 microfarad and a 6 microfarad capacitor in series, 1 by C underscore is equal to 1 by 4 plus 1 by 6 is equal to 10 by 24. C underscore is around 2.4 microfarads in parallel. It's just 4 plus 6 is equal to 10 microfarads. Understanding these combinations helps engineers design capacitors for tuning circuits, balancing loads, or storing large amounts of energy. Let's solve a real-world inspired example using everything we've just learned. Imagine a capacitor with plate area 0.02 square meters and plate separation of 1 millimeter. A dielectric with K is equal to 5 is inserted. What's the capacitance? We'll use the formula C equals K multiplied by epsilon naught multiplied by a divided by D. Substitute values. C equals 5 into 8.85 times 10 to the power minus 12 into 0.02 divided by 1 times 10 to the power minus 3. Simplifying the numbers step by step, you get C equals approximately 8.85 times 10 to the power minus 10 farads. That's 885 picofarads, a typical value you'd find in small electronic devices. This numerical brings together dielectric constants, geometry, and the application of the base formula into one elegant solution. So let's quickly revise what we've explored about capacitors today. A capacitor stores energy by separating positive and negative charges across an insulator. Its ability to store charge is measured as capacitance, defined by the ratio of charge to potential difference. This capacitance depends on the plate area, separation distance, and the dielectric constant of the material in between. We studied different capacitor types like parallel plate, cylindrical, and spherical, and understood how their structure affects behavior. And finally, we looked at how capacitors combine in series and parallel and tackled a practical numerical that brings it all together. Capacitors are everywhere in mobile phones, radios, car ignition systems, and even medical equipment. Understanding them opens up a deeper appreciation of how our electronic world functions. I hope you now have a clearer understanding of how capacitors work, from the math behind their storage to their role in real-life applications. Keep that curiosity charged. See you in the next session with another fascinating concept of physics.